We would like to solve this second order differential equation. So what we do first in such cases is this, that is, this is a second order differential equation in which the coefficients here are constants. So we will first take this homogeneous part of this equation, and then we are going to write a solution of this. So first let's assume that, just a moment, that we shall assume that y equals e to the power mx, where m is a constant, okay, so is a solution. And then what we would do is that we will substitute y equals e to the mx in this homogeneous part of this equation. So here we got e to the mx, its second derivative with respect to x, all right. And here for y we simply have this, so we got that. Now the second derivative, the derivative of e to the mx is derivative of exponential function is the function itself times the derivative of the exponent. So in this case, the exponent, when you differentiate it twice, will produce a coefficient of m squared for you by chain rule, all right. And here we simply have 3 times e to the mx, okay. And since the exponential function is never 0, all right, what will this yield is that m squared plus 3 is 0, okay. And so that tells us what? That m is equal to a plus minus square root of 3i because if you look at this, this means that m is plus minus square root of negative 3. Let me just bring it to the next line, okay. So plus minus square root of negative 3, and that just gives us that m is plus or minus 3i, taking I as a square root of negative 1. So now recall that when we have imaginary roots like this, we can use the Euler's formula, and I'm not going to go in details in this presentation because that was in the previous one. And in this case, the complementary function or the solution of our the homogeneous portion of the equation can be written as, let's just write yc as c1 times, okay. And now because this is square root of 3i, so what this will do is this will give us a cosine of a square root of 3x, and then plus, not plus in here, plus c sub 1, then c sub 2 rather, okay, cosine of a square root of 3x, okay. So this is our complementary function, all right. Now what we have to do is, and here is going to be quite a bit of work, that we have to assume, or we have to find a particular solution of this involving this right hand side function. So if you look at the form of this function, here I have a quadratic multiplied by an exponential, okay. So in the second derivative, what will happen? I mean, if we, so here, here we have 3y, and what I'm trying to talk is this, that we may assume that the particular solution is, okay, of the form a quadratic times an exponential function again. And the rationale for this is the following, that here is the exponential function that you can see. This is our right hand side, okay, quadratic times exponential. Here we will have that quadratic times exponential and then times the second derivative. So we'll substitute this and see if we get to any solution. Or or just do this, review what we had in the book, okay? That is what the trial particular solutions are. And of course, we are going to, just a moment, I have that on a different screen. Let me bring it up. Okay, so right here, I'm talking about this portion of the book, okay, where we have these suggestions for the particular solutions. So in this case, this fits in this category, okay, and we have to make sure that this power has not occurred before, which it has not, okay, and so then what happens is that we have this assumed as our particular solution. Now, the rest of the process will be just routine calculation. That is, if you go ahead, or rather just look at this, that you'll compute the first derivative of this function by using the product rule and of course the chain rule here. The solution will be, and I'm just going to pause and bring you the solution because it will take too much time doing all that basic calculation. So I'm just going to print the solution here for you, okay? And you can pause the screen and see if this makes sense, okay? Or I'm going to post a PDF on our website, a PDF copy of this. So either way you can proceed with this. And then what I'm going to do is that I'm going to bring you the calculation for the second derivative here. So the second derivative is, and again, I did the calculations, brought them here, just pause the screen and note it down, or go to our website and you can see it there. Okay, so we got the second derivative equal to this quantity and the first derivative equals this quantity. We don't need the first derivative in the original equation. So what we would do now is that we will look at our equation, and this the particular solution, or the particular integral as we sometimes call it, okay, it has to satisfy this equation. So what we have to do then is that go ahead and substitute these values in here, okay? So instead of going through all that algebra, let me cheat again and just bring you the calculations. So now we are going to just substitute this value and this value in the equation, and what that gives us is this equation, and we can just go ahead and collect the like terms. And then what do you see here? That in here I have negative 48x squared plus how many? No, x plus 0 as our constant. Okay, so if we match all the sides and do calculations the way we did for the case of partial differential equations, okay, what we will get is this. And I'm sorry, here you can see the screen is cut off a little bit, okay, that the equation looks like this. So if you now write or use the values of a, b, and c the way you obtain here, then the particular integral will be this expression. And now the solution can be written as that's what our method was, the complementary function plus the particular integral in this case. So that will be, what was our complementary function? The complementary function is right here. So you write that down and then plus what you have, plus you got this part. Okay, let me make it bigger again. Okay, so this is going to be the solution of the general solution of your differential equation. So let me know if you have any difficulty. All right, I shall try to clarify it.